I'd like to take a look at an application now looking back at position and velocity. We've studied those a lot. We'll continue to do the same. Now we'd like to take a look at how they deal with integrals and the fundamental theorem of calculus. So just to recall, the derivative of position is velocity. So then if we were to take the integral from a to b of velocity, remember the fundamental theorem of calculus says I will find the antiderivative of this. Or in other words, what function has a derivative equal to v of t? Well, we see from this s of t, right? S of t, the derivative of that is velocity. So this is going to be my antiderivative evaluated from a to b, and just using our rules, we have s of b minus s of a. So if I think about this, a is the starting point, b is the ending point. This is the position at the end, right? So this is my end position. And this here is my start position. So I take my end position, I subtract off the start position, and what that tells us is how far away are you when you ended from when you started. And what that is displacement. So this is describing displacement. How far are you displaced after some period of time? So to find displacement, to evaluate that, well, we just simply take the integral of v of t dt, where we have this time goes from a to b. So time's going from a to b, we have this. But if instead of displacement, I want to find how far total did I travel, right? Because if you think about displacement, let's say I start here, I do all of these crazy things, and I end back here. The displacement's very small, but the total distance is a lot. So what I need to do is I need to have everything be positive. I always need to have something positive and keep adding on positive things. So I'm going to change this by taking the absolute value of v of t. So the integral of velocity is the displacement. The integral of distance, or at least the definite integrals, the definite integral of the absolute value of velocity from a to b will be the distance. So if we take a look at this example, the velocity in feet per second of a particle moving along some path is given by this, t squared minus 4, where t is in seconds. What is the displacement? What is the distance? So displacement, we want the integral from 1 to 5. So the time goes from 1 to 5, those are our bounds, of t squared minus 4 dt. I just take the velocity. But for this one, I need to have the integral from 1 to 5 of the absolute value of t squared minus 4 dt if I'm looking at distance now. So if we think about what is the difference between these, how are we going to get different values? Well, for this first one, we just can use the fundamental theorem of calculus. I take the antiderivative of this, so I add 1 to the power of t, divide by the power. So I have t cubed over 3 minus 4t, evaluated from 1 to 5. I plug in the top number first, so I have 5 cubed divided by 3 minus 4 times 5. And I subtract off when I plug in 1. I have 1 cubed over 3 minus 4 times 1. So this would be 125 divided by 3. So I have 125 divided by 3 minus 20. And then over here, I'm going to get a 1/3 minus 4. So that would be a negative 11/3. So I would get a negative 11/3, but I'm subtracting that, so this would be a positive 11/3. So I get 136 over 3 minus 20, or again, finding common denominators, this will be 60 over 3, so I would get 76 over 3. And this displacement is in feet, right, because that was my units. Now what's going to be different is that we need the absolute value. We need to figure out when is this positive and when is this negative, because different things happen when it's positive versus negative. So if we think about this curve looks like the following. Oops. Down here, this is negative 4. Where it crosses over here is going to be at 2. So my curve is negative on the interval -1 to 2, it's going to be below the x-axis. But then when I go up to 5, I'm going to be above the x-axis in all of this. So I'm going to split this integral up where it changes from positive to negative. So I'm going to have the integral from 1 to 2. No, this should be positive 1 over here. Integral from 1 to 2. If this is all going to be negative, I need to negate this to make it positive. So I'm going to have a 4 minus t squared dt. And then I add on the integral from 2 to 5, and this is just going to be a positive value, so that will stay the same. So this is similar to the other absolute value example we looked at, except now I don't just have the absolute value of x. I have t squared minus 4, so that's either positive or negative. Now I do the regular thing that I just did. I take the antiderivatives, so I have 4t minus t cubed over 3 evaluated from 1 to 2. And then over here I have t cubed divided by 3 minus 4t evaluated from 2 to 5. So I plug in 2. I'm going to get an 8 minus an 8/3 minus 4 minus a 1/3. And then over here, if I work with this, I'm going to have a 5 cubed beside is 125 over 3 minus 20 minus an 8/3 minus an 8 by plugging in 2. And now we just simplify all of this. We have a whole bunch of these terms that we're going to be working with. So if we just deal with the fractions over 3, I have a negative 8/3 plus a 1/3. That will be a negative 7/3. Plus the 125s, that will be negative 118 or positive 118 over 3 minus an 8/3. So that would be 1/10/3. So I have 110 over 3. And then my constant terms will be an 8 minus 4. So that will be 4 minus 20. That will be a negative 16 plus 8. That will be a negative 8. So then finding our common denominators again, this would be over 3, that would be 24. So this would be a 86 over 3. So this one, and again, this is in feet. So we always expect the distance to be at least larger than the displacement. It has to be, it could be the same, right, if you just go always in a straight line, but because this is moving in a slight parabolic motion, indeed, the distance is a little bit more than the displacement, and that's good. So those are the slight differences between distance, displacement, when we're looking at the relationship with velocity and position.